Have you ever looked at a photo on your phone and pinched the screen to get a closer look? Notice how the picture gets bigger, but the bird itself doesn't stretch or warp out of shape. In the physical world, making something bigger or smaller without ruining its shape is a very real challenge. Take a tailor in downtown Kampala. He might have a tiny paper pattern for a child's shirt, but he needs to make the exact same design fit a fully grown adult. Or think about a carpenter working in Boise. If he wants to build a huge dining table, he might build a tiny, cheap wooden model first to test the design before risking expensive wood on the final product. The solution to both of these problems is a process called scaling. When we make a design larger, we call it enlargement. When we make it smaller, it's a reduction. Mastering this process allows designers, engineers, and local makers to solve tricky physical problems on a simple piece of paper, long before they spend money on final materials. To scale something accurately, we rely on a mathematical rule called the scale factor. This is simply the number we multiply every single dimension of our object by. If we choose a scale factor greater than 1, like 2 or 3, we are making the object bigger. This gives us an enlargement. If our scale factor is a fraction less than 1, like 1/2, the object gets smaller. That is our reduction. You will often see this written out as a ratio. A helpful trick to remember which number is which is the phrase drawing to reality, or D to R. The first number is always your drawing, and the second is the real object. So a 1:2 ratio means the drawing is half the size of reality. A 2:1 ratio means the drawing is twice as big. The scale factor acts as a universal translator. It ensures that whatever you sketch on a tiny notepad perfectly matches the true proportions of the real world. So how do we actually draw this on paper? Professionals use a highly accurate drafting technique called the radial line method. Let's look at this sketch of a traditional grass-thatched hut to see how it works. First, we place a single point anywhere outside our original shape. We call this point the pole, or the center of enlargement. Next, we shoot light, straight lines starting from the pole and passing directly through every important corner of our hut sketch, like the roof peak and the bottom edges. Now for the math. Let's say we want to double the size of the hut using a scale factor of 2. We measure the distance from the pole to a corner on the original sketch, multiply that distance by 2, and mark a new dot further down that exact same line. We repeat this for every single corner. Finally, we connect all these new dots together. The result is a perfectly scaled, larger version of the original design. This radial method removes human guesswork. It relies entirely on geometry, guaranteeing that your scaled-up design will function perfectly when you go to build it. When learning to scale, beginners often fall into 2 traps. The first is about angles. Even though we made the sides of our hut much longer, the internal corners did not change. A 50-degree roof peak in the small sketch stays exactly 50 degrees in the large version. Scaling only changes side length, never the angles. The second trap is about area. Look at this simple 10 cm by 10 cm square. If we enlarge it by a scale factor of 2, it is easy to assume the total space inside only doubles. But let's expand the sides to 20 centimeters. Look what happens. It actually takes 4 of the original squares to fill the new space. Doubling the sides quadruples the total area. This is why builders must be incredibly careful with their math. If a painter thinks the scale factor of 2 means buying twice as much material, they will run out halfway through the job. Scaling is an exponential multiplier. This image is a vintage map showing the Lake Victoria region. Mapping an entire geographical area onto a single piece of paper requires a massive scale reduction. It allows us to hold thousands of square miles in the palms of our hands. Conversely, when workers paint a massive billboard on the side of a brick building, they are using extreme enlargement. They take a piece of art that fits on a desk and scale it up by an enormous factor to cover multiple stories of a wall. Whether going up or down in size, the rules are strict. A scale factor above 1 enlarges the design. A scale factor below 1 reduces it. And through it all, the shape's internal angles will always stay the same. From a custom-tailored shirt to a sprawling highway map, the built environment relies on this exact mathematical relationship. The biggest creations around us all start with a simple drawing and a precise scale factor.